Last week it was announced that a star, HD 139139, was found to be behaving very strangely in the Kepler 2 data. It was as though 28 planets, all but one about 1.5 times the size of Earth, passed in front of the star. But at random, they did not appear to be periodic, as you would expect with orbiting planets. Today I'm joined by Dr. Andrew Vanderburg, one of the scientists trying to unravel the mystery of this star.
Welcome to Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Andrew Vanderburg. He received his PhD in astronomy at Harvard University in 2017 and was a postdoctoral associate at the Harvard-Smithsonian Center for Astrophysics until he started his Sagan Fellowship at the University of Texas in Austin. His research focuses on extrasolar planet detection, in particular, studying the Kepler Space Telescope data.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Dr. Vanderburg, welcome to the program.
Thanks for having me.
Now, Doctor, you have discovered in the Kepler 2 data a very, very strangely behaving star. Can you give us an overview of this star?
That's right. We've discovered a star that is called HD 139139 that we call the random transitor, which appears to have dips in its brightness, like the ones you would expect for planets that cross in front of their star. But the weird thing is that none of them seem to line up, and none of them seem to correspond to multiple orbits of the same planet.
These dips look like planets, right?
Yeah, they look just like the dips that you would expect for planets to create. They just don't seem to come at the right times.
Which suggests that whatever this is, it isn't periodic, right?
Right. Or it's either so complexly periodic that we haven't figured it out yet.
Now, that would require a whole lot of planets, though, wouldn't it? Because you only observed with the Kepler 2 mission for, 87 days?
Yeah, that's right. We observed for 87 days, and we detected 28 dips. And as far as we can tell, none of them, or at most a handful, seem to line up with one another. So that would require something like 14 or 15 planets if we were to imagine that all of those were caused by planets.
Do you have any data on how distant they could be from the star if they are periodic? I mean, could they be very far out and just slowly passing in front of the star as they orbit very slowly? Or do you have any indicator that they might be closer to the star?
Yeah, so we have a few pieces of information about each of the dips. One of them is the depth of the dip, or how much light is blocked. That roughly tells us the size of whatever object must be causing this dimming in brightness. We also have the duration of the dip, or how long the dip lasts. And this is what gives you some information about how far away it might be from the star, because the dip gives you roughly the speed at which the planet is orbiting the star. Now, there are a few factors that can affect this, but generally, we see dips that last from a little bit less than an hour up to 8 hours. And those tend to be corresponding to planets in orbits fairly similar to the ones we see around other stars with planets detected by K2. They don't appear to be really, really distant if they are a little bit further out than usual.
Now, the star itself, this is a type G star, so it's somewhat sun-like. How close is this to the sun?
It's pretty close. We can measure the temperature using our spectra that we took from observatories like Fred Whipple Observatory and McDonald Observatory. And we measured that the temperature of the primary star, this is a pair of binary stars, is about 5280 or 5220, depending on how you measure it, plus or minus about 5200 Kelvin. And that puts it right around where we know that the sun's temperature is, which is about 5777 Kelvin.
Can you tell if these objects are orbiting that main star or the secondary star in the system?
No, we can't tell. They're so close together that in the Kepler data, they all fall within the same pixel. So it's very difficult to distinguish which star is the source of the transits. To make matters worse, in this data set, Kepler is moving back and forth over time, which makes it even more difficult to figure out which star is causing the transits that we see.
So could that be a solution, that maybe you have some sort of bizarre situation where you have some planets orbiting one star, some planets orbiting another, and maybe that could be causing the non-periodic appearance of the star system?
It's possible, but it's still pretty tough to make that work. For one thing, if you had some planets orbiting one star and some orbiting the other star, you still might expect to see periodicities. There could be bunches of planets orbiting each of the stars, but that situation starts to strain credibility a little bit. And the reason is that if all of the planets, or if some of the transits were on the fainter star, the planets which cause those transits would have to be bigger to cause that same amount of total light lost to take place in the system. So if they were around the smaller star, they would have to be roughly Jupiter-sized. And if some of them were around the bigger star, they would have to be about the size, 1.5 to 2 times the size of Earth. So that's a lot of coincidences, because you now have to have large planets on one star, small planets on the other star, that all added together, when you add together all of the flux from the system, give you transits of about the same depth. So that feels a little bit difficult to make work. It's a little bit contrived.
Now, that's one of the interesting points of the stars, that all of the dips appear to be about roughly the same size. So if these are planets, except for one, they're all roughly the same size.
Right.
What could explain that? Is there some other explanation? Like, for example, say you have a disintegrating planet or something like that. Could that throw out dust in such a way as to appear that way?
It's possible. So we only know of a handful of disintegrating planets, 3 disintegrating planets around main sequence stars, and 1 around a white dwarf. And one of the characteristics that's common to all of these objects is that the depths of their dips change quite a bit. They can go from 0 depth, basically no transits at all, to their full depth over the course of just a few orbits. And that's one of the reasons why this is a potentially attractive way to explain why there are no periodicities. Maybe most of the time, those dips are just gone. You don't see anything coming out, and then occasionally there's a poof of dust, which causes a transit that then goes away very quickly by the time the disintegrating object comes back around for its next orbit, and you just lose your periodicity that way. The problem, though, is that you might expect to see dips in between the full depth, which roughly would be about 200 parts per million in this case, and 0. It's maybe possible that there are some of those that we miss, just because once you get to a much smaller than about 200 parts per million, you're hitting the noise floor of the Kepler data. It's just too noisy to detect things that are much shallower than that. But it's still a little bit hard to imagine based on what we know about disintegrating planets today.
How can you rule out dust in this case? What observations can you make? For example, can you look at light and see if it absorbs blue light and red light differently and try to determine if this is dust or if it's solid planets? Is that the next step in observation of the star?
Yeah, that's potentially another step we could take, although there may be some wrenches thrown into that as well. If you imagine that dust is causing these dips, then potentially, yes, if the dust particles are small, then you would see that the transits should be deeper in the blue light than they are in red light. And that's what we've seen for objects like Voyager's star. Mm-hmm. But when we've tried to do this for disintegrating planets, we haven't necessarily seen this. And we've come to the conclusion that maybe the reason that we don't see it is because there are no small dust particles, because they were so small that they sublimated away thanks to the intense radiation environment. So if this is a disintegrating planet very close into its star that's very hot, then we may not see that color dependence of the dips like we would for something further out, like we imagine is going on around Voyager's star.
So would that be like basically big rocks coming off of the planet, and any small stuff just gets disintegrated and blown out, but you still have chunks, essentially, of the disintegrating planet?
Yeah, it doesn't actually have to be that big of a rock. Anything larger than a few microns would be very difficult for us to detect wavelength dependence for. Roughly, the size of your particle is the wavelength at which that dependence starts to turn on. So if you have particles that are even maybe 10 microns or larger, we just don't have observational resources to make those observations well and see that there's a difference in the depth below the size of that dust particle and above the size of that dust particle.
Now, in reading about this star and reading your paper, one thing struck me is that there seems to be some sort of fundamental issue with every explanation anybody's thought of so far. except one, which might be the idea that this star has sunspots on it that are very short-lived. Tell us about that option.
Yeah, so that would be a new thing. We know that there are sunspots on our sun that appear and they live for a few months, a few times the sun orbits, a few rotation periods, and then they decay away. And we see star spots on this star in the light curve, or we infer that they are there based on the light curve because they behave similarly. We see this slow modulation of the brightness of the star, which is characteristic of star spots that last a long time. So you see these large dips. They're roughly the same depth as the short transit-like dips that we're seeing. This is pretty common. We see this in thousands and thousands of stars in Kepler where we have long-lived spots. What would be unusual is if the spots were to appear very quickly over the course of maybe 30 minutes to an hour, last for anywhere between 30 minutes to 8 hours, and then disappear just as quickly. That would potentially explain these transits. Now, it's not like anything we've seen on the sun, and it's not like anything we've seen in any other Kepler stars. So we have that problem to contend with. But as far as we know, there's no reason why it couldn't be. The main reason we included an explanation like that is just because we, as you said, noticed that all of the other explanations we could think of had some flaws. And this one doesn't. There's really no reason we can think of why this can't be the case, but there's also no good reason for us to think that it is the case. So it's a little bit out there. It's maybe a little bit of a shot in the dark, but maybe it'll turn out to be correct.
Well, it's kind of interesting because since the star is so sun-like and it's younger than the sun, as I recall, it's only 1.5 billion years roughly, that might yield clues on the earlier history of the sun. Maybe the sun did produce sunspots like this and it somehow, as it aged, stopped doing so.
Yeah, it's possible. You would expect if this was something that all stars did, that we would have seen more examples of this, though, before. So it seems likely that this is, at the very least, kind of an unusual star, and maybe this is an unusual process if it is something intrinsic to the star.
Now, uniqueness is always noteworthy within astronomy because if you only see one example of something, then it seems a little weird. Out of, hundreds of billions of possibilities, you only see one. But is there anything close to this star that's been noted before, other than, of course, Boyajian star?
Not to my knowledge. We've seen a lot of weird transits. As you noted, Boyajian star, we've seen the Differ stars around young stars, which showed very similar dips to the one around Boyajian star, but we know that there must be dust in the system from the protoplanetary disks. We've seen transits that only happen once or twice that could be caused by planets. We've seen some that have happened only once or twice or happened aperiodically that are shaped funny, that make us look like comets. The weird thing about this system is that the transits are otherwise very planet-like. They're symmetric, they're about the right depth for some of the most common planets in our galaxy, super-Earths. They're about the right duration for planets on relatively short period orbits, like the ones that we expect to see transiting. It's one of these cases where if you didn't look at anything but the periods, if you just looked at that light curve by eye, you would say, oh yeah, that's a multi-planet system. And only on closer inspection do you see how weird it appears to be.
The TESS spacecraft,
yeah,
which I know is going to be looking close in, but some people say it's going to be taking data that might be useful for objects further away, which, for reference, this object is about 350 light years, something like that.
Yeah.
Are you going to be able to use TESS to study this?
Not anytime soon. So right now, TESS is conducting its primary mission, where it observes most of the northern sky and most of the southern sky. It's already finished most of the southern sky, and it's about to flip to the northern sky right around now, I guess. And it's actually looking out a part of the sky right around where this star sits. And that's because TESS is a satellite, not a spacecraft orbiting the sun like Kepler. And TESS has to contend with the Earth and the Moon, and it can't look where those bodies are. And this object happens to be very close to the ecliptic plane, the plane of the orbit of all of the bodies in our solar system. So TESS is actively avoiding looking at this area of the sky for now, and it probably won't be able to get there until extended missions in the future. when the orbit of the spacecraft is favorable for it to look in this part of the sky and not have Earth or the moon come in and swamp the detectors.
I see. Now, are there any other instruments, including coming instruments like the LSST, that will be useful in studying this?
Yeah, so the challenge with other instruments on the ground is that the transits are very shallow. When Kepler detected them, it was only about 200 parts per million. It's basically impossible to get that kind of precision from the ground. Now, if the dips were on the secondary star, the fainter star, then they would have to be much bigger to produce an average depth of 200 parts per million, and that actually might be detectable from the ground. So one thing that we could do is we could use a ground-based telescope that has better spatial resolution, that takes sharper images than Kepler did. And we can look for transits of the fainter star and see if there are transits corresponding to large planets on that star. And if that's the case, then that A tells us which star it's on, and B gives us a path forward to maybe unlocking some sort of pattern in the timings of the dips, or some sort of periodicity. If the transits are on the primary star, though, then we really have to stick with spacecraft. So Spitzer would be an option, but Spitzer is about to reach the end of its lifetime in about 6 months. The European Space Agency is about to launch the Cheops telescope, which may be our best bet. And if we really think we understand something and we can try to predict when we might see a transit, we could use something like the Hubble Space Telescope or the James Webb Space Telescope. The problems with using those two is that it's really hard to get a lot of time on it. And if we didn't know when to look ahead of time, it would be very difficult to convince other astronomers that we should spend a month of Hubble time looking at this one star when we don't even know whether we're going to detect anything that'll help us understand the mystery.
It's rather unfortunate. I missed the Kepler spacecraft. I think we should have manufactured them and sent a whole bunch of them out looking at do an all-sky Kepler survey.
That would have been fantastic.
Yeah, because I out of all of the missions of the last decade, Kepler really yielded a lot of mysteries.
Yeah,
you know,
absolutely.
Very strange stars. And how many exoplanets did it discover? Like 2,400, something like that?
At least, yeah.
And so it's a resounding success for a mission that really wasn't that expensive compared to others.
Absolutely.
Now, with HD 139139, there is one last option, and it's the very last option, the bottom of the barrel that you don't want to go to unless you absolutely have to, which is SETI. Is there a SETI possibility with this star? Could this be something completely out there?
I would have to say there's no reason why it couldn't be. And you could even tell yourself a nice story about why it might be. As you said, it's kind of our last-ditch possibility. You know, we astronomers have a long history of finding something weird like pulsars, like Voyager's star, scratching our heads over it, not having a good explanation, and then thinking, oh, well, maybe this is some sort of extraterrestrial civilization. And then realizing later, no, we have a good natural explanation for this, and we can figure out what's going on. I suspect that this star will be another one of those cases. But in the meantime, I think it's perfectly acceptable to consider the SETI hypothesis.
Absolutely. And it reminds me and this is entirely speculative, but it reminds me of Luke Arnold's paper with, he described back in the 2000s this idea of transiting structures that are just obviously appear artificial, like a louver or something like that can be picked up in a light curve.
Right.
Now, my thought is, well, what if you make the appearance of an impossible star system? Would, presumably alien astronomers see that with their Kepler spacecraft and say, that can't happen in nature, that has to be artificial. Is that a possibility here?
I think it's possible. I think that the Arnold paper focused on unusually shaped objects, which would give you transits that don't look like planets. In this case, they actually do look like planets, to the best of our ability to tell. Maybe with even higher precision data than what Kepler was able to give us, we could have noticed some unusual behavior at the very beginning or the very end of the transits, which could have distinguished circular planets from, triangular or star-shaped structures. So it would have to be a little bit different from that hypothesis as well. Yeah, I could imagine that this kind of thing could be some sort of signaling beacon. If you can build stuff like that, it would probably be a lot cheaper to leave that in orbit for a long time. than it would be to continually broadcast radio signals.
Yeah, especially if you're blasting out omnidirectional signals in like contact, and that just takes a massive amount of energy. But if you just made something look weird, whether it's just a star system that physically shouldn't exist without technology or something like that. So, but there's no indication of that yet. We're not to that stage yet, but it's interesting to think about.
Yeah, for sure.
Now, another striking thing about this is the randomness of this star system, as though these planets we're passing could have been generated by a random number generator. How does that play in?
Yeah, really, that is just a statement of our inability to find any periodicity. A lot of things can approximate a random number generator, and this thing approximates it very well. But we only have 28 dips, so it's not very strong for us to be able to say that it is random. Probably there is an underlying pattern. We just can't find it with only 87 days.
One other question regarding the SETI possibilities. If it were something like that, what would you look for to try to determine if that was it? Would you look for some sort of pattern long term, in other words, study the star for a year and see if there was anything there? Or would you try to get spectra of whatever these objects are? How would you go about determining, or say they were planets actually, say they were planets and you wanted to study the planets themselves and try to work out what their atmosphere might be like? How would you go about doing that with this star?
So the first thing that I would do, if I had the resources to do it, would be to build a new Kepler to go and observe this star for much longer than 87 days. So in the original Kepler field, we had data on stars for 4 years. Now, after the mechanical failure that ended the original Kepler mission, we only were able to observe stars for about 80 or 90 days at a time. I think that if we had been able to observe the star for maybe 4 years, we might have been able to detect some patterns, and we might have been able to figure out what was going on. So if I had the resources to do so, I would just keep monitoring the star, record all of the times of dips, and just keep doing the tests that we did in this paper until some signal starts to emerge from the noise. Then, if they're planets and we think we have a period, you can come in with more powerful instruments like Hubble or James Webb, and you can look at the spectra of their atmospheres to try to figure out what was going on. It's just very difficult to deal with objects where you can't predict the next event. It makes everything a little bit less efficient. Instead of being able to come in with James Webb and spend maybe a couple of hours when we know the transit's going to happen, you would have to spend, days. On average, there were about 3 days between each transit, which is pretty tough if you want to spend a lot of time with James Webb. You would have to observe for several times that to guarantee with some high probability that you would find an event.
One thing speaking of KSE 8462852, that star, they crowdfunded observation time on, I suppose, private telescopes.
Yeah.
Is this possible to do it with HD 139139?
It's possible. We could try to observe it from the ground using the same telescope network as a Voyager star. Unfortunately, the small depth of the dips would hurt us there as well. If we found out that the dips were on the fainter star, then that would open up that possibility quite a bit, and we could do something exactly like Voyager star and try to just pin down as many dip times as we could and maybe eventually find a period.
Now, in terms of these dips being shallow, how much of a percent is the drop in overall light? I know with Voyager star it was like 21% or something like that, but in this case it's much smaller. So percentage-wise, what's it like?
It's about 2% of 1%.
Oh, so very dim.
So
yeah, very, very
200 parts per million.
I see. Now, how big are these? Say they're planets. How big are they? I mean, are these Earth-like sized planets? And I know if they're around one star, they're going to be Jupiter-sized, but say they're around the other star, how big are they going to be, and are they within the habitable zone of the star, if you can tell?
Yeah, roughly they would be about 1.5 to twice the size of Earth, which is a fairly common size for planets. We've found with the Kepler telescope that these super-Earth-sized planets are some of the most common planets in the galaxy. Based on how long it takes for the transits to happen, what the duration of the transits are, I would guess that most of them are probably too close in to be in the habitable zone, but maybe some of them could be. In particular, there's one dip that lasted 8 hours. That's getting to the orbital speeds that we expect for a planet in the habitable zone.
Now, one odd aspect of this is that if you were in this star system, HD 139139, and you turned your Kepler spacecraft towards the sun, you would see our solar system transiting, right? Which would put it,
That's right.
puts it in like 0.5% of the galaxy.
That's correct.
It's interesting.
That's one of the things that you could use to make a really nice SETI case if you wanted to.
Yeah, they look and they see this beautiful exoplanet Earth, and they're like, well, let's orient something towards them and send them a message.
Yeah.
Out of how many stars within Kepler's second mission field of view, is this one out of how many that you saw?
That showed patterns like this?
Yeah.
In the second mission, there were probably 300,000 stars observed.
Mm-hmm.
And as far as we can tell, there were no other stars like this. It's a little bit hard to say that for sure, though, because this was not found by computers. This was found by humans, citizen scientists, looking through the data by eye. And what's great about humans is that they learn as they go along. But that doesn't necessarily mean that they were looking for this very early on in the mission. Maybe they wouldn't have seen it if they'd come across it. So it's possible that there are other objects like this in the data set that the citizen scientists may have passed over the first time they saw it, and then as they learned more about the data and what was interesting, may have passed it along to professional astronomers like myself when they saw it at the fairly close to the end of the K2 mission when this object was observed.
Now, what was the citizen science project that found it? Was it the Planet Hunters that I know they found Voyager's star?
Yeah, so this is a group working independently. I believe they all started out on Planet Hunters, and they learned very quickly what was interesting, and soon the Planet Hunters online interface just wasn't enough for them, and they started writing their own tools. They have this freeware package called LC Tools that lets them very easily click through light curves very quickly and look at them and zoom in and measure things. It's a very impressive operation, and there's about 10 or 15 of these folks who just do this, and whenever they find something interesting, they shoot astronomers like myself an email and say, hey, look at this.
I think it's a wonderful thing, because astronomy has always been something where the amateurs could help the professionals. Mm-hmm. Back in the day with people searching for comets with telescopes, a lot of them were just amateurs with telescopes.
Yeah.
And now in the computer age, we can do much, much more. And that sort of symbiotic relationship continues. So one last question before we go. Say that if you had to make a bet, what explanation is the best? The sunspots? And if you had to make a bet, do you think that's really what it is? If
I had to make a bet, I would go with my first instinct. When I first saw this light curve, I said, this is a multi-planet system. And even though it seems really hard and contrived to make that work, the transits look too normal for me to believe that it's some sort of dusty thing. We've never seen any indication that a star spot can appear and disappear the way it would need to in this case. None of the other explanations feel right to me, other than something to do with a transiting planet. There may be a twist. There may be a binary planet. I don't know. Some sort of weird architecture. Maybe some sort of glitch like a flare in the star that happened at the time of a transit, which made us miss one. Something weird may have happened. But my guess is that somehow the final explanation will end up looking like a normal transiting super-Earth around the primary star.
Should the various SETI programs turn their radio telescopes to this star?
I think so. SETI is, by its nature, a high-risk, high-reward observational program. I would say that looking at stars like this has very little downside for them. If they find nothing, then they mark that star off the list. There are lots of other stars, but I think this one has a much better reason than most other stars in the galaxy for them to look at it. So I would say, why not? If we find it, if we find something there, then it's the greatest discovery in the history of our civilization. So what is there to lose?
Nothing to lose, and even if we don't find it, we still have one very interesting star system that's going to teach us about something new.
Absolutely.
Well, thank you for joining us, Doctor, and good luck with your research.
Thank you for having me.
This has been a breaking news story from Event Horizon. Be sure to subscribe for updates on this as well as regular guest interviews every Thursday.